In section 1410, we've already discussed the nucleophilic ring opening of epoxides under basic or strong nucleophilic conditions, where your nucleophile contains a -1 formal charge on the nucleophilic atom. Now we're going to be talking about acid catalyzed ring opening of epoxides. In acid catalysis, you have a neutral nucleophile attacking. Here we just need to worry about two. We either have neutral water attacking or a neutral alcohol attacking. Okay, so your weak nucleophile is going to be water. So there's no formal charge of -1 there, so I'm not writing Nu minus, I'm just writing Nu with a lone pair. And we have water, okay, or an alcohol. All right, and as we'll see here, the nucleophile is going to attack the more substituted carbon in an SN1 type transition state or an SN1 type reaction. I should probably say SM1-like because in this reaction, we are also going to get inversion of stereochemistry, okay? Inversion. Okay, so in yellow, those are basically the highlighted cliff notes of what you need to know for this last part of the section 10 in the textbook. So let's take a look at some reactions now. So let's take ethylene oxide and treat this with water under acid conditions. Remember, we place a catalyst under the reaction arrow. So here you just need a drop of H+. That'll be enough to convert a tanker car full of ethylene oxide and excess water, of course, to produce ethylene glycol. We can also treat this with methanol and acid. Methanol and acid is going to add methanol to the epoxide, and that's going to give you so in these yellow boxes, I am highlighting the part of the molecule that comes from methanol. Okay, so the H and the methoxy group both arise from the methanol that's used here. Okay, so let's just take you through the curved arrow reaction mechanism here. In general, when you have acid in a reaction condition, always use acid in the first step of your mechanism. We're going to use it here to protonate the oxygen of the epoxide. Okay. So when we protonate something, we use the letter P to help us remember that's the elementary step occurring here. Next, we have water attacking. Now, in the case of ethylene glycol, either carbon is equally substituted. So oops, I forgot to draw the intermediate. Now, this molecule here, this intermediate oxonium ion, is extremely reactive because of ring strain and the polarity between the carbon-oxygen bond, and we've also protonated the oxygen to make it a very strong nucleophile. So something neutral like water, which is an extremely poor nucleophile generally speaking, is really going to attack this quite readily now. And you can attack either carbon atom of the ethylene oxide because they're both primary. And when it attacks, we say A for attack. And we're going to get two carbons. We're going to get an OH on the right the carbon on the left is going to be bonded to water. Remember, water carries in with it 2 hydrogen atoms, and so this molecule here is going to have a formal charge of +1 on the oxygen atom. Next, we have to deprotonate this oxygen atom, and we can do that with the solvent, okay, water. And that's going to give us the, in this case, a diol, right? All right, so the first step is protonation. The second step is attack. Here we're showing water, it could be an alcohol. And the third step is going to be deprotonation. So those 3 steps can be summarized by PAD, okay, or PAD for short. So those are the abbreviations to help you remember the curved arrow reaction mechanism, okay? Now, an alcohol can do the same thing, as I mentioned, and you need to watch out for substituted carbons, and you need to watch out for stereochemistry as well. So let's make this an isopropyl group there, make it really interesting looking. Okay, I'll draw some hydrogens on the right and also on the left carbons. So let's take a look at this molecule here, and we're going to treat this with, let's do ethanol and H+. And let's try to figure out what the reaction products will be. So when we do this, we need to identify the substitution level of each of the carbons, and we count how many carbons are bonded to that carbon. So this carbon that I've dotted purple is bonded to 1 carbon, so we say it's secondary. And this carbon on the right that I'm dotting green is going to be secondary because it's bonded to 2 additional carbon atoms. So we say it's secondary carbon. Now that's the more substituted carbon atom, okay? So let's take a look at what happens here. In the first step, you guessed it, we protonate the oxygen atom of our epoxide. Takes a while to draw out, doesn't it? All right, so now we have this oxonium ion, and we want to think about what is the structure of this. You could write this in different ways. Some textbooks show a resonance arrow, but I like to think about more about the charge distribution here. So we know that oxygen is normally delta minus, and carbon is normally delta plus. So it seems weird to write delta minus on top of an oxygen atom that is plus in this Lewis structure, right? But remember again, oxygen is sucking electrons towards it relative to the 2 carbon atoms, okay? So if it's helpful to think about this, let's erase the delta minus on the oxygen, and for sure put delta plus on the oxygen, on the carbon atoms. Now, which of these carbons is going to be more delta positive? The more substituted carbon is going to be more delta positive relative to the other one, because the more substitution you have on a carbon, the more that those groups can stabilize a carbocation. So it's probably better to illustrate this molecule with a longer carbon-oxygen bond to the more substituted secondary carbon, and a shorter carbon-oxygen bond to the less substituted one. And that's going to place a greater delta plus on the right carbon and a smaller delta plus on the left carbon, okay? Remember again, this is an extremely reactive intermediate. The positive charge, there's ring strain, there's electronegativity differences, and we want to spread this charge out that's burdening the molecule as best we can. So that delta plus is going to be shared around by different atoms in this molecule, and it's going to be more shared on the carbon atom that can more stand it, okay? The one that's more substituted has a surrounding isopropyl alkyl group that can help stabilize that positive charge through something called induction or hyperconjugation, if you remember back in chapter, I think it was 6, okay? So what that means is that the nucleophile, which is in solution, is going to attack the right carbon atom, okay? So let me copy this on the next page and we'll continue from there, okay? So our nucleophile here is ethanol. I'm going to draw it out so we don't get confused with the lone pairs and the atom involved here. So here's my oxygen atom with 2 lone pairs, and it's going to now attack this carbon and kick off that oxygen, okay? Now that bond is rather long. The carbon-oxygen bond, as I mentioned in this reaction intermediate, is very long, but it's not quite a carbocation. So we're not gonna get top attack and back attack. We're gonna kind of have it attack SN2-like, SN1-like. It's debatable how you wanna call this. Now I'm switching gears. I'm saying it's gonna be SN2-like in the terms of inversion of stereochemical information, okay? So we get inversion, and in this sense, it's SN2-like because you have an inversion of configuration. So we're going to get the OH coming off as a leaving group. We're going to point it up to the upper left. And we're going to draw our ethanol here that's come in from the bottom right. So that's on the opposite side now. So that's how we say it's inversion. And our isopropyl group is going to be on a wedge, and our hydrogen is going to be on a dash. And now we do some administrative workup. We take our ethanol and we remove this proton here to give us the neutral organic molecule. And here I'll simplify the ethyl group and I'll just write it as ET, all right? So starting from, well, that's not the starting alcohol, but we get this guy here, okay? And that's inverted, okay? So when you have 2 different carbons, you want to attack the more substituted carbon, and you want to realize that there's an inversion of configuration at the more substituted carbon atom. Okay, so let's look at one more example here. All right, so we have water and H+. Remember, H+ is the catalyst. And so we're not going to do the mechanism here. We're just going to think through and figure out where things go and what the stereochemistry is. So this carbon right here is tertiary. This carbon right here is secondary. Okay? So this is the carbon atom that we want to attack. Now here, the carbon-oxygen bond is going up. So when we get the product, we want the carbon-oxygen bond to be going down, okay, going down. So I'm going to draw OH here. Remember again, the water molecule is a source of the OH. On the tertiary carbon, we want to draw in those groups. We have our methyl that's on a wedge, our ethyl that's on a dash. The thing we've inverted is that yellow highlighted bond. So that's how we say it's inversion of configuration. On the right carbon, we don't change anything. The hydrogen is still pointing on a wedge. The ethyl is still pointing on an ethyl. And the carbon-oxygen bond is still pointing up on the screen. It's twisted over a little bit, but it's still pointing towards the top of your device. And so we write OH here, okay? If you wanted to spend time looking through R or S, Well, this is not one I can easily do in my mind, so I'm not going to say if it goes from R to S or S to R, but it does invert if you spend the time to figure this one out, okay? Problem 20 asks us to draw the product and the mechanism. I just want to draw the product, but believe me, working through the mechanism is something that you need to repeatedly do to gain skill, to remember why something attacks here and so on. And so let's look at this first problem A here. We have HCl. HCl is an acid. So you can guess that it's going to be acid catalysis. Now look at the molecule. Oh, they're both primary carbons, so we didn't need to worry about if it's acid or base. Now what's being added? We're going to add HCl. Why? Perhaps working through the reaction mechanism might help you do that. So I take that back. Let's do the mechanism for this one. First, we protonate. Then we have chloride attacking. Okay? So that's how we get chloroethanol in this case here. All right, how about in molecule B? We have the same thing happening. We're going to protonate, that's how we get the OH, and then we have bromide, which is going to attack. Bromide is going to attack the more substituted carbon right here, and it's going to do that from the opposite side of the leaving group. Remember, the oxygen atom is the one that's leaving. That's on this side of the molecule. So bromide's going to attack from the opposite side, which is the lower right-hand corner of your device. Okay, so what we're going to get is, this is answer A. What we're going to get is our leaving group is going to be the OH, and our bromide is going to be here. The bromine atom is going to attack from the lower right-hand corner. The methyl group is still on a wedge, and the hydrogen is still on a dash. I'm not going to draw the hydrogen because it's not drawn in the starting material. Okay, so that's going to be the product there. Okay, so HCl adds an H, adds a Cl. HBr adds an H, adds a Br. H2SO4 is in brackets here, and that means it's a catalyst. I like to just put H plus below the reaction arrow, and I like to put the actual reacting solvent or whatnot above the arrow. So we know we're going to add ethanol to this molecule. We're going to change it to an OH, and we're going to put an ethoxy group on there, okay? So again, we examine the more substituted carbon atom. It's there. And so that carbon is going to incorporate an ethoxy group, ETO, okay? The other carbon right here on the right side is going to have the OH group, okay? So keep in mind that ethanol is a source of ethoxy and it's a source of hydrogen, okay? And now the busy work is to figure out where all those other groups are. Now we've attacked the circled carbon here, so I've taken care of the stereochemistry by drawing the OET to the bottom left. So I just need to sketch in the other two groups that still maintain their wedging and dashing, okay? On the right carbon, we did not attack that stereogenic center, so it's retention over there, okay? Molecule D, we have the similar kind of thing. H2SO4 is just the source of H+. They like to show it in brackets, and we have H2O. So H2O is a source of OH on one of the carbons, and then we place the H on the oxygen that used to be the epoxide. So again, we have a more substituted carbon on the left, and we're going to attack from this direction, okay? And so when we draw the OH from the water molecule, it's going to be towards the bottom left of the screen. The OH on the top right comes from the starting oxygen atom in our molecule. The wedge here is still a wedge. The wedge here is still a wedge. And the dash here is still a dash. Okay? So you can see the pattern here. If we have things on wedges, we keep them all on wedges. If we have things on dashes, we keep them all on dashes. The important thing to remember is that the incoming nucleophile we have to place opposite the bond to the oxygen of the epoxide, okay? So if the bond to the epoxide is this way, we have to draw the line to the incoming nucleophile like ethoxy or hydroxy in the opposite direction, okay? Let's do one more here. So here we have H plus and methanol, and we're going to attack this carbon right here. So what do we need to do? We need to draw the incoming nucleophile off on this direction. Okay, so the MEO is over here. All right. On the right carbon, we draw the leaving group still in that direction. We leave alone all of the wedges and dashes. So the methyl is still on a wedge. And then we have this 1, 2, 3, 4. It's called a spiro. So that spiral ring system, we just leave it as is. We have a wedge, we have a dash, and we have those 4 carbons, okay? That's not a stereogenic center there, so you don't need to really worry about messing that up, okay? In molecule F, we have HBr. We've seen this before. This is the more substituted carbon atom. So remember that our nucleophile is going to attack from this direction, okay? So we are going to take the bromine and draw it in that direction. The leaving group is the oxygen of the epoxide, right? Which has an OH group from the hydrogen from the HBr, which protonates it. The stereochemistry on the right, we leave it wedge dash. The stereochemistry on the left, we've inverted it by making the bromine to the bottom left. So we can just draw in the wedge ethyl and the dash isopropyl group. Okay, so that in a nutshell is how acid catalysis works. You want to protonate the oxygen, use a neutral nucleophile or something very weakly basic like bromide to attack the more substituted carbon atom. There is inversion at the more substituted carbon atom. So I hope this brief tutorial kind of helps you get started on the homework and any kind of reading you have in your textbook. Thanks for watching.